Yes, looks good, thanks. Okay, this is all right. I can see it. All right, we can start. So just so you know, if you have not watched one of the last two lectures, there should not be so much overlap, so much dependency. So I'll try to make it kind of independent of the previous lecture. We'll talk a little bit about Gaussian wave functions, but not so much, and you saw it in the tutorial anyway. Okay, so today we started talking about the Stern-Gerlach experiment last time, and today we'll continue. But for this, we're going to introduce a more general topic, which is these measurements as physical evolutions. We talked about it before. And now we're going to see an explicit procedure. So the procedure we're going to do, it has many names. Normally it's called von Neumann procedure for indirect measurements of some observable, and then we'll do the application to our experiment. So the lecture notes should be online already. If they're not, then they'll be in the next few minutes. So last time we started talking about this Stern-Gerlach experiment, and just to recap what the idea is that we want to measure the spin of, or some internal property of a particle. It doesn't need to be the spin. The spin works in magnetic field. So let's say the spin of an electron, but we cannot go there and measure it directly. What we can measure is the position of the electron by making it hit some screen, and then we just, here there'll be some reaction and we can see what's happening there. And the way to do this is to make it go through some interaction region where there's some magnetic field. B is the word for magnetic field. So here comes our electron. Oh, good. It interacts with magnetic field, which will couple the degree of freedom, will couple the spin to the position or to the momentum of the electron, and then depending on whether the spin is up or down, the electron will go to the right or to the left, and then we're going to measure it there or there. Okay. So just to make this, I'll make it just what the goal is a bit more clear, and then we'll see what is happening in this region here. Okay. And maybe before that, now I'm giving you like the rules, like the experiment of how to measure a spin, but you can imagine the first time someone shot an electron through a magnetic field, they might have been quite surprised to see that the electron will bend either to the left or to the right. And this was like one indication that there's some property here that reacts to magnetic field, and that's what the spin is. So just to recap, we have our total Hilbert space is going to be 1 qubit for the spin of the electron. And then we have the position Hilbert spaces. And for now, we're just talking about 2 dimensions. So h of x, h y, right? The order in which we put them doesn't really matter as long as we keep track of what subsystem is. In the initial state, so psi times 0. And now, in the previous lecture, we saw the evolution here. When there's this free evolution, and this becomes a bigger, if it starts in a Gaussian here, it becomes like a wider Gaussian over there. But for now, we're going to start right here with a Gaussian because it's just simpler. So we have some state that we don't know, which you can expand in the 0, 1 basis. So these are unknown coefficients. I mean, we know that they're numbers that we want to measure. And then we have here some initial state on X and Y, which is a Gaussian moving in this direction, right, in the Y direction. Okay, so this is our initial state. And now the goal is to design some Hamiltonian for this region here, such that after this evolution, the spin is correlated with the position degrees of freedom. Okay, so I'll just write it down again. So the goal design some interaction Hamiltonian such that after some time t of being in this region, then with some evolution, such that u of t applied to my initial state is going to be something like this. So where these are two different wave functions, and this one is kind of a wave function in this direction, so a Gaussian moving in this direction, and this one is going to be a Gaussian moving to the right. Okay. Because the goal is that then we can put here a screen, and then we see, well, if it comes here to the left, it corresponded to this branch of the wave function, and if it comes to the right, then it corresponds to this branch of the state. Yes, question. Design, sorry. Yes, so H int interaction Hamiltonian. So the thing is that in this region, in this interaction region, what's going to be the total Hamiltonian? Well, we can't get rid of kinetic energy. That's just the way the world works. So we still have this H0 plus H int. This is the thing we want to design. This will be what corresponds to having the magnetic field there. And this is just nothing on the spin plus p squared over 2 mu on the x and y. Right, this is our standard Hamiltonian of the free particle. Sorry, it is a product, yes. Right, but the idea is also that we make this much, much larger than that, which is not hard because, you know, the mass is very small here. So this term is relatively small. So we want to say we make this matrix much, much larger than H0 so that U of t is approximately, you know, for small times, it's approximately just e to minus I. Okay. And we're going to take for now as if the Hamiltonian was just this H int. For the interaction region, yes. Yes. So, you know, yeah, there's a way to design like the whole the whole global Hamiltonian as just one thing, but you can think, for example, that I turn on the magnetic field and then I turn it off again. So it's just during this time. Or we can say that the magnetic field is only valid in this region of Y, which is a bit more annoying to treat mathematically, but that's a good exercise for the tutorial. So maybe I'll ask Nuriya to do this next week. Okay. So today we're going to see how to define this Hamiltonian in general, then we see how it acts on general states. And then next time we will see what happens exactly in this evolution after interaction region to this wave function and this wave function. Okay. So now what I'll say is general for any measurement we want to do that you want to perform indirectly. So one, so now, suppose that you have two Hilbert spaces. And this is the system that you want to observe, like the spin, for example. And this is the system that you actually can observe. So this is what I call a pointer. So for example, we cannot observe directly the spin, but we can observe the position of the electron. Or for example, I cannot measure the temperature outside directly, but I can look at the people and what they're wearing and infer the temperature from there. It's the same kind of idea, right? So this is the thing that we can observe directly. And this is the thing that we can't. Okay. And we want to measure some observable on system S. And now we're going to look at the simplest case where S is a discrete system. P doesn't matter for now. But let's say, so for example, the spin, so this is a discrete system. We'll have some observable, so it has a discrete number of eigen states, AK. You know, this could be degenerate or not, but this is our projector, and this is our label. So that's what we want to measure. For example, in the case of the spin, we could measure the spin in the z direction, which is h bar over 2, 0 minus 1, which is just a z, Pauli z observable times a constant. Okay. Okay. And say that we have some initial state that we want to measure. Well, we have some state that we don't know on the system to be measured, like our spin state. There, we didn't know these coefficients, alpha and beta. It could be more generally any state here. And we have the initial state of our pointer, which we should choose well, okay? So this, for example, we can choose this to be like a little Gaussian, which is the case here. And now this state, we might not know it, but we can expand it in the basis of the observable, right? So we can expand this as these coefficients alpha k depend on the state, and then we have ak. Right? I didn't do anything. I just wrote it in the same basis that the observable is diagonal. And now here's the proposal for the Hamiltonian. Int. Well, this is the observable one to measure. This is just a constant that we can tune, and we'll see later what the effect is of this. And this is going to be some, oh, there's a p, some operator that acts on p on the pointer, which we will choose later. Okay. So this is the first time we see a Hamiltonian that is not just something in the first system times the identity on the second plus the other way around. This time there's actually something in both systems at the same time. Okay. So now we need to see what is the action of u of t on the initial state, right? On so to do this, now we need to go through some maths, which are not hard, but are not that inspiring either, okay? But just so we know like what the idea is, and the idea is that we're going to end up with the kind of correlated state between the two systems. In fact, maybe I'll write it here already, what the final state will be, so that you're going to get this times some state here in the pointer. And this is going to depend on B and on the coefficient. We'll see what this is later. So now we need to write down this unitary, and then we need to apply it here. Yep. And the whole goal of this is just to prove that this designed Hamiltonian works. So we do it, right? U of t e to minus I into t h bar minus I t g h bar, and then we have s sub b t. And then why not? I'll do this right away here. In the lecture notes is in a different order, but I'll do it right away. So we just expand this exponential. Okay, we just do the normal Taylor expansion of the exponential. So we write it. It's always the same trick. And factorial, this thing to the n. And then we have s to the n, b to the n. And now, what is this to the n? Well, as is defined over there. Maybe I do it here on the side. So as to the n, sum over k to the n, which in principle could be many terms, but because all of these ak's are orthogonal, this is just sum over k, ak to the n, and then the projector. Okay, so we write this here. And for reasons that will be clear later, we pull the sum outside. So we have the sum over k first. And then we have the sum over n. And then this whole thing. this acts on system S. Okay. Yes. Where's the typo?
We have take part on the AK, but not on the capital graph.
Well, because when you do it, so let's say you only do it twice. For example, you end up with AK, AK prime, AK, AK, AK prime, AK prime. But this is delta K, K prime, right? So you actually have like many terms, but they all cancel out each other unless K equals K prime. So then yeah, change that. I mean, another way to look at it is to see, look, this is the diagonal version of the matrix. Oh, this is the matrix already expanded in the diagonal basis where you just have this 0, 1, 2, and so on. And when you do this to the n, you just get the ends here because the other are valid.
What conditions can we write the unitary?
This is the Hamiltonian, it's independent of time, so you have uniform dynamics, so the unitary is this. That's it. Okay. What happened?
Can we go right thing down?
So here it looks okay. Are you sure?
Just some message I saw right now, so it was from 12. So
Yes, no, it was the yeah, the camera died at the end of the tutorial. I think it was right at the end. Okay. Okay, so now we can apply that thing to the state. So then we have that u of t applied to my state. And it's going to be, let's write over k. To the n, and then we have this is this whole thing applied to my state, which we expanded in this basis, right? So it was alpha k. So k prime. Okay. So as usual, tensor product. This operator acts on the first space, and the other operator acts on the second space. And on the first space, we have this AK in a product with AK prime, which we know. Again, this is the Kronecker delta, right? And on the second half, we just have this BP and this thing. So let's simplify this whole thing. Okay. n, ak to the n, alpha k. And then the only surviving term on this side was this ak, right? On S. And on the other side, we still have b to the n. Good. Now, this whole thing here, this is just a number, right? So if it's a number, it doesn't matter if it's on this side of the tensor product, or we can just move it to this side of the tensor product. So that's what we do. We just move it all to the other side of the tensor product. And then this is nice because we end up with some k, alpha k, ak on the first. And then in the second one, we have this sum. This whole thing. Okay. And what's nice is that this again is just the expansion of an exponential. So we start with an exponential on both systems, and now we move it to an exponential just on the second system. So I'll write it again, what this whole thing is. Now we have equals sum over k, alpha k. Okay, tensor. Now exponential of what? Okay. B. On system B. And we just call this. Okay. So look, the thing we're acting on the second system with an operator, but this operator is multiplied by a value that depends on the eigenvalue of our observable. And the goal is going to be to choose, we're going to choose all these parameters that we're free to choose. So we can choose G, we can choose the time of the interaction, and we can choose what we apply here in the on the second system, such that these states for different case are more or less orthogonal, right? Maybe they won't be perfectly orthogonal. Yeah.
So there's someone where does it reach
So here's you have a sum over the whole thing, right? But the only terms that depend on n are these and then this. So we move them all to this side. It's just a number, right? If I have 3, 0, 1, I can write this as 0. It's the same vector, right? I can move this number from this side to the other side. That's clear? Okay. Then I just grouped here all the elements that depend on n. Doesn't change anything. Still associative. Yeah. And then I just said, just a moment, Evan. Well, this is just the expression for the expansion of an exponential. And then I just replace it with the exponential there. Yes. In this case, we're looking at k being finite, yes. So we're saying we're measuring, so the system S is discrete, like our spin system.
Yeah, but
It could be 2 qubits, it could be any system of dimension d, yeah. No, this is, okay, so this is more general than just for the electron. This is, you're trying to measure any discrete system. In fact, the calculation is almost the same if you do a continuous system. Then A is a continuous observable and you just redo everything with integrals instead of sums. Was it more or less clear for you?
My issue is more say that the green part is a number.
Yeah.
That's not the whole part, right? Because you kind of missing out on the B in this one.
Yeah, but this is an operator. This needs to stay here in the second system. This is a state needs to stay in the same in the first system.
Yeah, no. My issue is to say this is a number, and then you move that down to that thing.
Yeah.
And then you capture the.
I mean, again, if I have 3 times 2 here, I can just put a 6 on this side, and it's still the same. And everything is associative and linear and nice, so I can put the brackets wherever I want. Yeah.
Because the issue is because if you do it like that, you say that part is a green number. Like I agree, that's a number. Yeah. But I mean by that you're kind of missing out the fact that BP is also part of the sum. And
yeah, everything is part of the sum, but I just look, think of it of just I take, instead of moving that there, I take this here. Okay, I take this 2 here because they don't depend on n, so they can come out of this sum. Okay, and now I'm really just moving the sum from here to there. That's allowed. I did not destroy the sum or anything, right? BP was inside the sum and it still is inside the sum. Okay. So now the goal of the whole idea of choosing a good measurement is that we choose all these parameters that we could choose. So the initial state of the pointer, what operator we apply here, for how long, how strong we make our Hamiltonian, such that at the end, these states are kind of orthogonal. So for example, one example will be if my initial state of the pointer is here, then at the end of the day, I have 1 here and 1 there. So this would be the K1 and the K equals 0, for example. So that then I measure, for example, the position of this, okay? And if I'm here, I know that I'm in this blob. Here, I know I'm in that blob, and there's a small probability some overlap. In fact, there's a whole field of quantum theory that is about tuning these parameters and seeing about, well, maybe, and there'll be an exercise about this. If I don't choose this so that they totally overlap, but I choose them such that they are like something like this, then maybe, if I get a result here, I don't know from which component it came from, but on the other hand, this will disturb the state less. This is something we'll treat maybe in a tutorial, but for now, we'll see the example. Yeah. And the example is just applying to the system we want to measure. So in the Stern-Gerlach experiment, what is the observable we want to measure? In this case, it's just a qubit, and we want to measure Z, for example. Or you could choose like just the Z observable or put any other numbers here. Doesn't matter so much. But this is what nature gives us. So it turns out that when we turn on the magnetic field, what happens is that it couples the spin to the position operator. So we could have chosen, for example, here to put the momentum, and this would give us something different. But what nature gives us is that it's this. So our H int, some G, S and Z on S, and position on X. Okay. And for now, in Y, we do nothing, okay? So I can even write here that there's nothing happening in the Y direction. So what is our unitary after some time t? Well, e to minus I t g h bar z x. And for the identity, and we've seen this before that we can take identities out of the exponential. Okay, so this we did some weeks ago. Good. And what's our initial state? So we will justify this next week, but it's going to be, so alpha 0 plus beta 1, and this correspond to, in our observable, alpha 0 and alpha 1. And then we have this Gaussian, and we will justify this next week, but the Gaussian can be seen as a Gaussian over X. That's the product with the Gaussian over, let's give it a different name. On Y. So if you take the Gaussian into the wave function, like we did it before, you can see that it's a product of the one on X and the one in Y. So we can do it like this. So what's the final state? We just apply what we did before. So the final state, well, it's going to be some our k is the number of values in the, sorry, the number of eigenvalues of the observable. The observable is diagonal in the 0, 1 basis, so it's already written in the right basis. This alpha k are alpha and beta respectively. K on S e to minus I t g. These ak are plus and minus h bar over 2 x. And nothing happened to y, so this is the thing we're going to call phi k. And now we need to look at what this is like. Right, so far I just applied that directly for a specific choice of B and A. And the only caveat was that there's an extra system here, but there's nothing happening there. Good. And now this turns out to be quite an important operator. And yeah, in general, most measurements that are done, at least in experiments that involve particles moving around, either this, like the interaction is either with the X operator there or with the momentum operator. So this is quite general and keeps popping up in different places. So let's just simplify the notation. We have phi k is e to, let's write minus I L where there's like 3 constants here, so let's just gobble them up in one, and then later we can change it for the specific results. Okay, this operator here is called modular position, and there's equivalent modular momentum, but this doesn't matter so much for you right now. So what to do is we expand this state here. Okay, so we have E minus I L X H bar, and then we expand this state in the position basis. So we move this inside. E minus I L X H bar. So now this we've done many times. This operator is diagonal on the X basis, it's acting on the X thing, so on the X state. So it just returns the X, E to minus I L little x, so this X. Okay, we have this. And now at this stage, we cannot tell much about what's going on here. So we look at it in momentum basis. Why do we do this? Because we have this coefficient here that looks nice for when we do the Fourier transform. So in momentum basis, yeah. Sorry, yes, this is equals. This is the definition. I mean, I just called it this. Yes. Yeah. So let's call, I mean, this is the state again, and this is the new wave function. Or say k, right? So in momentum basis, what we have, if I want to know momentum for some p, well, I just do the Fourier transform. H bar usual coefficient 2 pi H bar. And now I replace this. The X E to, what did we get? Minus I L X. And now it's the usual trick, right? That we did already, I think, earlier this week. I just group this two and I get E minus I X over H bar, and then if I have P plus L. And this now is the Fourier transform of the original wave function, but not at momentum P, but at momentum P plus L. This is little p, by the way. So this is of the original wave function of the pointer before we moved at P plus L. Good. So this is a good point to stop, because we'll see later what this means for the Gaussian wave function. But if you look at it already. Remember that this L depends on the coefficients AK. So if you look at it in momentum space, then what we get is like, if this was your average momentum just when it started, then you have like kind of, you get two blobs, one corresponding to the eigenvalue. And now I don't know the direction very well. I think it's the other way around. If I measured, if the spin was 0, it comes to the left. If the spin was 1, it goes to the right. And like the whole area covered here is going to be alpha squared, and the whole area covered there is going to be a squared. And this is kind of of P, sorry, P of the final state. So what happens when we couple the thing we want to measure to the position is that it splits the momentum wave function into two, so it gives a shift to the wave function in a direction. If this observable had more eigenvalues, then you might get another peak here, another peak there, corresponding to the different eigenvalues, right? If you're not measuring a qubit, but something larger. In the case of the Gaussian, what this corresponds to is that this one is going to be a Gaussian moving to the left because this is momentum, right? The momentum is going to the left, and this is going to be moving to the right, and then we can observe this on our screen. This is very general for how one can perform measurements. Good. So next time we'll see how our Gaussians evolve now, and then we'll look at the double slit experiment, which is a bit different. All right. Thank you, and see you on Tuesday. Yes.